The Boeing 787's engines are technological miracles most passengers never think about. Revolutionary fuel systems, record-breaking pressure ratios, engineering breakthroughs decades in the making. Here is the insane technology powering the Dreamliner. The jet engines of today are barely recognizable to those of the 1940s. They are bigger, they are more powerful, they are more efficient. The Dreamliner engines are so big that they are the same diameter as the 737 fuselage. This is just part of the puzzle that has allowed the 787 Dreamliner to break world records. In March 2020, in the midst of a global pandemic, the US government imposed travel restrictions on all European travelers. This move cut off France from one of its far-flung territories in French Polynesia. Business as usual for Air Tahiti was no more. A creative solution had to be found to replace the regular flights between Tahiti International Airport and Charles de Gaulle Airport, which, under normal circumstances, stopped over in LAX. Faced with disruption, Air Tahiti began operating the world's longest flight, a 16.5-hour, 15,700-kilometer non-stop flight between Tahiti and Paris, the world's longest distance scheduled flight. And it was technically a domestic flight. The 787 made that possible. Today, we are going to learn how. All of that work on the airframe is useless without a power system to match. Boeing transformed the way airliners are powered to create a plane like no other. The first step in powering a large plane is to get the jet engine started. That itself is a very power-hungry process. We need to get the compressor section turning in order to achieve adequate compression for engine ignition. We have all seen footage of people hand-cranking old piston-powered planes to get them started. This obviously is not feasible for jet engines, which need to rotate at very high speeds to start. Engineers have dreamed up many ways to complete this job. Some engines use explosive cartridges that look like shotgun shells that will be fired by an electric charge. The hot gas expelled by the cartridge then drives a smaller turbine, which is connected to the drive shaft through a reduction gear, allowing the smaller turbine to get the engines up to speed. Cartridge starters were popular in older military planes that may need to get into the air on very short notice with limited ground support. Some planes like the SR-71 had a direct drive starting car which connected two massive V8 engines directly to the J58 engine from underneath the nacelle to get the powerful jet engines up to 4,500 RPM. However, air starting is by far the most common method, where pressurized air is fed into the turbine section directly to get the engine moving. This can be done with an external cart called a huffer cart, which connects hoses to the engine. But most commercial airliners are capable of generating their own pressurized air with an APU or auxiliary power unit. These are smaller turbine engines located at the tail of the aircraft that are small enough to get started with a battery and an electric motor. Most people are not even aware this mini turbine engine exists, but you can see the exhaust on all modern commercial airliners. The 787's APU, like other planes, is started by a small battery, but from here, the 787 system architecture is very different. The 787's APU does not provide pressurized air to the engines. It provides electric current to two electric motors attached to each engine, which act like the starter motors on your car. However, these motors can act as generators to provide the 787 with unparalleled electric power. A traditional plane has one generator on each engine and one on the APU, but the 787 is anything but traditional. There are in total 6 generators on board, with 2 pairs on each engine providing the main power, each capable of generating 250 kilowatts, with 2 more on the APU providing secondary power, each capable of providing 225 kilowatts. If all 6 of these generators were running at the same time, that would be 1.45 megawatts of power available to the 787, 4 times more than a 777 is capable of producing. To put that into perspective, if we needed to generate that electricity with solar panels in the middle of the day, we would need to cover about 10 football fields with solar panels. This is a lot of power. So why did the 787 need that much power, and where is it all going? The 787 uses a no-bleed air architecture. Traditionally, many aircraft systems are powered by hot compressed air drawn from the compressor section of the jet engine. The APU normally provides hot air to the engines to get them started. Then, once the main engines are started, hot compressed air bled from the compressor section drives several important systems. Normally, air conditioning and cabin pressurization is handled by the bleed air system. The bleed air would be drawn from the engine at a temperature upwards of 230 degrees Celsius. This obviously would quickly turn the cabin into an oven. So the air would first run through a complicated air conditioning and pressurization system, where some of the air is cooled using a heat exchanger, which uses outside air from a surface-mounted intake called ram intakes to remove heat from the engine bleed air until it is a suitable temperature to be distributed through the cabin. So we are doing work to remove energy from this valuable bleed air from the engine. This is obviously rather inefficient, and all that ducting is heavy. This is why the 787 does not use this system. Its cabin pressurization is handled entirely electrically. We now have two inlets, the ram air inlet and the cabin air compressor inlet. The cabin air compressor inlet leads to, you guessed it, the cabin air compressor, an electrically driven device that compresses the air for the passenger cabin. This compression process heats the air up too much for direct use into the cabin. So it does require some cooling, using a heat exchanger cooled by the ram air inlet. You can see this little door open while the plane is on the ground. It serves to protect the inlet from foreign objects entering it. Another energy-intensive process that has been handed over to the electric motors is the braking system. As you can imagine, the energy required to slow down a 200-ton plane traveling at 270 kilometers per hour is not small. The vast majority of that energy needs to be dissipated by the brakes of the plane. Reverse thrusters can deploy that redirect air from the bypass ducts through slots that open on the side of the engine. So the brakes need to convert a lot of kinetic energy into heat energy. You can really see this in effect during a plane's most extreme brake test, an aborted landing test. Here the plane is flying at full load and has to stop using brakes alone without reverse thrust or other aids. The brakes get so hot they glow red and can even catch fire. Traditional braking systems would dissipate this energy as heat through friction brakes. But the 787 uses regenerative braking similar to electric cars. The electric motors on the engines can act as generators during braking. They convert kinetic energy into electrical energy, which is then dissipated as heat through resistor banks or used to power aircraft systems. This reduces wear on friction brakes and improves overall efficiency. Now to the engine itself. The GEnX engine represents a quantum leap in turbofan technology. At its heart is breakthrough fuel injection technology that took 26 years to develop. The challenge was achieving higher compression ratios without creating excessive emissions. Higher compression directly translates to better thermal efficiency and lower fuel consumption. The GEnX achieves a pressure ratio of 58:1. This is record-breaking. But higher compression leads to higher temperatures. Higher temperatures result in increased emissions of potent greenhouse gases like nitrogen oxides. Nitrogen oxide formation rates rise exponentially with flame temperature. To facilitate increased pressure ratios while hitting climate change goals, this problem had to be addressed through ingenious fuel injection technology. The compressor feeds its high-pressure air into 22 fuel mixing nozzles located in a ring around the compressor exit. Their job is fairly simple. Mix the fuel into the air and ignite it. A simple job that started development in 1995 with both General Electric and NASA. The art of crafting the perfect fuel injection nozzle is incredibly complex. A delicate yet violent process like an orchestra whose crescendo is a fiery explosion. With the advent of 3D printed manufacturing, GE has been able to create a fuel injector with a complex internal labyrinth of air channels that traditional tooling simply could not cut. The fuel injector they developed is called the Twin Annular Pre-Swirl Injector, or TAPS. It avoids dangerous nitrous oxide emissions by carefully controlling the air-fuel mixture ratios to control flame temperatures. Previous injectors would start with a rich air-fuel mixture, then dilute to a lean mixture. The problem is the fuel goes through the stoichiometric region in between these two phases, creating a great deal of nitrous oxides. The TAPS fuel injector uses a large amount of air in the premixing phase to ensure thorough mixing and a lean air-fuel mixture. The combustion process starts in the lean zone and gets even leaner further into the combustor, never getting close to the peak nitrous oxide production region. This may seem like a simple device, but it took generations of design iterations with computer simulations gradually bringing engineers closer to their target. None of their designs would have been possible without current generation metallic 3D printing that could manufacture the complex parts with materials capable of resisting the enormous heat within the combustor. 26 years of development paid off with 60% nitrous oxide emission reductions. A fuel injector compatible with the record-breaking 58:1 pressure ratio used in the GEnX. GE managed to increase the pressure ratio even though they reduced the number of compressor stages. The GEnX contains 10 stages, 4 fewer than the CF6 engine it is replacing. GE managed to do this through new, improved blade design. Finding information on this topic was incredibly difficult, a testament to how advanced and secretive the technology is. The compressor includes 3 blisk stages, which are perhaps the most impressive feats of machining imaginable. Traditionally, compressor stages are made by attaching the blades to a separate disc with dovetail connections. This decreases manufacturing complexity. But the dovetail connection is less durable, increases assembly and maintenance costs, and allows some air to escape through the connections. Blisks are compressor stages manufactured from a single piece of metal, making them stronger and easier to install while improving aerodynamic efficiency. The turbine section also made use of new material science breakthroughs. It was the first commercial engine to make use of gamma titanium aluminide, an advanced alloy of titanium and aluminum that combines the heat resistance of titanium with aluminum's weight savings, replacing the nickel alloys of the past. It took 3 decades to take this material from the lab to commercial use. The Dreamliner was the first plane to make use of it, paving the way for the material's acceptance in the industry. All of these factors combined to allow the GEnX engines of the Dreamliner to reduce fuel consumption by 15% over previous generation engines. That is an astronomical leap. And on top of all that, the engine is 60% quieter than similar sized planes, in part thanks to the engine's most distinctive feature, the sawtooth pattern on the fan casing and the engine exhaust. These features are called engine chevrons. They are not just futuristic cosmetic design, but functional parts of the engine that significantly reduce engine noise. Because turbofan engines force air out of their bypass chambers and turbines at speeds much higher than ambient airspeed, the air interacts with the free stream air, causing mixing. This mixing causes uncontrolled vortices, which generate excessive noise for both passengers and the community on the ground. Think of it like water accelerating down a waterfall and striking the water below. That turbulence can be extremely loud. The chevrons aim to control the vortices shed from the engine nozzle by creating smaller vortices at each of the teeth of the chevron. This allows the hot, fast air being expelled from the engine to mix with the ambient air more gently. This is said to reduce jet blast noise by as much as 30%. It allowed Boeing to use substantially less sound insulation in the fuselage walls, which helped reduce aircraft weight. The 787 truly does live up to its name. It provides a passenger experience almost incomparable to other commercial aircraft, with advances in noise reduction, fuel efficiency, and passenger comfort. The 787 could be the most advanced piece of engineering in commercial aviation. And it is a plane many of us will have the opportunity to fly in and marvel at the decades of engineering advancements that made it possible.